Hello students, let us continue our discussion on current electricity, and this is the 41st session. The last session is 40th. I mentioned it as 41st, it was a mistake. So this is 41st session and the chapter is current electricity. In the last session we were discussing about Kirchhoff laws, right? Particularly the discussion was, the last session we discussed about Kirchhoff's second law, which deals with the EMF in a closed path, right? We chose a mesh, electrical mesh, right? Or we say mesh of an electrical network, which includes various devices like the cells, resistors and all. And then when we go through the cell, when we go through the path of the connection throughout the mesh, right, from one point coming back to the same point, we got an expression for which we got an expression which relates that the resistors, the resistances and the EMFs of the cell in the mesh. So that expression is obtained using Kirchhoff's second law, right? And today we are going to discuss a particular network, okay, a particular network which is useful in practical applications, and it's also useful in many theoretical implications. So one particular network or one particular electrical network that we are going to discuss today or understand about it is Wattsons network. So this is a network which involves, or this is an electrical network which involves 4 resistors connected in a quadrilateral form with a galvanometer and an EMF. Okay, this is the basic arrangement. Basically, Wattsons network is an electrical network. Okay, you put some resistors, put some EMFs or cells and all in a circuit. You design in a way whatever you want, that will become an electrical network. And similarly, this Wattsons network is a particular network which has 4 resistors, 1 cell, 1 galvanometer. The use of this Wattsons network is to find an unknown resistor, find the unknown resistance of a resistor out of these 4. Okay, you will get to know how are we going to get the expression for the unknown resistance in the network. But for now, the application of this Wattsons network is to get the unknown resistance among those 4 resistors. Okay, we will have 4 resistors and we can get the resistance of one resistor using the resistances of other resistors. We will see how are we going to get that. And let me give you the pictorial representation of the Wattsons network, which looks like this. So as I say, it's a quadrilateral basically. Okay, it's a quadrilateral with 4 resistors. Let me name the quadrilateral first. The quadrilateral shall be named as A, B, C, D. Okay. Now here between the terminals A and C, I am going to connect a cell, and between the terminals B and D, I am going to connect a galvanometer. Okay. Basically, what's a galvanometer? It's an electrical device which shows the presence of current. Okay. If there is current flowing through the galvanometer, it deflects. If there is no current flowing through the galvanometer, it doesn't deflect. Okay, it's just a device to show the presence of electrical current. That's it. No need to worry about much of it, because we are going to discuss about galvanometer in detail in the coming chapter. Now, where are the resistors? Resistors come in the edges of the galvanometer. So one of the resistor will be there between the points A and B, the other resistor will be there between the points B and C, the other here between C and D, and finally the fourth one between A and D. Now we are going to name the resistors. The first resistor here between A and B is named as P, and this is named as Q, and this is named as R. Okay, P, Q, R, S. So this naming is very important. You shouldn't go in the order. Okay, P, Q, R, S. No, don't do that. There is a reason. You will get to know why by the end of the derivation that we are going to do. But for now, you keep this much in mind. Name the resistors as P, Q, R, S. P, Q, R, S. Okay. So this is the pictorial representation of Wheatstone's network, which involves 4 resistors P, Q, R, S connected in a quadrilateral form with a cell of EMF E between the terminals A and C, and a galvanometer between the terminals B and D. Okay, good. Now there are few considerations that we need to do here before we start the derivation. But before we go for the considerations, we need to know what is the balanced condition of this galvanometer, of this Wheatstone's network. Okay. So when the entire Wheatstone's network is balanced, okay, we call that as balanced condition of Wheatstone's network. When do we say so? Okay, so it is somewhat like a flow of water again. See, here you have 2 pipes. Here those 2 pipes are connected to 2 more with a pipe in between these 2. Okay, just imagine the flow of water. Now if the resistances, okay, are balanced properly, then the current will flow directly from P to Q and R to S completely without entering the galvanometer. Okay, that is what is called balanced condition. When do we say the Wheatstone's network is balanced? We say the Wheatstone's network is balanced when current through the galvanometer is 0. Okay, so this is the balanced condition. So when there is no current flowing through the galvanometer, the Wheatstone's network is said to be balanced. Okay, so this is the basic base in which we are going to derive the expression for the relation between PQ and PQ, R and S. Okay, clear on that? So when do we say the Wheatstone's network is balanced? When the current through the galvanometer is 0, we say the Wheatstone's network is balanced. Right. Now we'll assume few things here. We'll consider the considerations are as follows. Okay, see, since we have connected a cell, it will be supplying EMF to the network, and hence there will be current in the network. Okay, so let I be the total current that is due to the EMF, due to the cell connected here, and that current splits here. Okay, because you have 2 wires connected at this point, so the current splits. When the current splits, it goes as I1 and I2. Okay, it splits as such. Then it reaches this point, the point B, and from the point B, the current again splits. Right, wherever you get a split of the network, a split of the conductors, there and all you can expect the split of current. So this I1 comes here and splits into, let me call Ig be the current flowing through the galvanometer in this direction, and let the current I3 flows through Q, and this I2 comes here. Okay, I2 comes here, and again it splits at this point, but this time we have current already coming in this part of the galvanometer or in this part of the electrical network like this, right? So now what happens is these two currents join together and go through the resistor S, and let me call that current through resistor S as I4. Now I3 I4 together comes to point C and becomes the same current I and comes back to the cell. Okay, this is about the considerations about current flowing through the network. And one more consideration is, let G be the resistance of the galvanometer. Okay, even though galvanometer is an electrical device, basically it's not a resistor, but every electrical device will have its own resistance. Okay, let small g, let this G itself be the resistance of the galvanometer considered here. Clear about that? And one more question that might rise is, why does the current Ig is in this direction itself? Why not like this? Yes, it is possible. Okay, because if I2 is dominant over I1, getting? If I2 is dominant over I1, which means I2 is greater than I1, then after when it comes to this point, when they split, Ig will be, the current Ig will be pushed in this direction. Okay, and since here we have stuck to one particular consideration where I1 itself is dominant over I2, and hence Ig is flowing in this direction. Okay, again it also depends on I3, I4 and all, but no need to worry. The direction of Ig is not going to affect the final result of the derivation. You will get to know, because you can get the Ig direction exactly in the opposite way and do the derivation again, you will get the same result. Okay, fine. Now we need to get the relation between P, Q, R and S. Okay, right, let us go for that. Now we will make use of Kirchhoff's voltage law. Are you clear with the considerations? Here P, Q, R, S are the four resistors connected as shown in the figure with a galvanometer between the points B and D and a cell between the points A and C. Now let I1 be the current through P, I2 be the current through R, I3 be the current through Q, I4 be the current through S, and Ig be the current through the galvanometer G. Now I be the total current. This total current does not matter for us. And one more important consideration is, our principle of the Wattsons network is, we say the network to be, Wattsons network to be balanced when the current through the galvanometer is 0. Okay, when you have 0 current through the galvanometer, we say the network is balanced. Clear on that? Fine. So now let us move ahead for the derivation, and we will apply Kirchhoff's voltage law for two loops which we find in the network. Okay, the first loop that I am going to take is, okay, I am now applying Kirchhoff's voltage law KVL for, look at this, how many loops do we have here? If you observe carefully, here we have we can get 3 loops. One is A, B, D, A, right? This is one loop, and the other loop is B, C, D, P. This is the other loop, and we have one more loop which is A, D, C, A again. Okay, A, D, C, A. So we have totally 3 loops available in this network, and we are going to consider 2 loops out of that. One is this loop, the other is this loop, and we will apply Kirchhoff's voltage law for those 2 loops. Now applying KVL in for this particular loop like this. Okay, right. Now you see it is A, B, D, A, right, and I have also chosen the direction. You know very well, I can either go clockwise or I can also go anti-clockwise. That doesn't make any difference in the expression that we obtain. Applying KVL for the loop A, B, D, A, okay, A, B, D, A. So, let me start from point A and move along the path. So, when I am moving along the path, I first find the resistance P, right, and we have current flowing through the resistor I1, and hence now I should take the product of current flowing through that and the resistance of the resistor, right. So, now I should take I1 P, because you know very well the Kirchhoff's voltage law says sum of EMFs in the network in a loop is equal to sum of product of current and resistances, right. So, since there are no EMFs here, EMF part will be 0 and the other part left will be simply the product of currents and resistances. So, okay, let me go with the actual formula. It's actual definition of KVL. Algebraic sum of EMFs. Is there any cell here in this loop? No loop. So, it is 0. Algebraic sum of EMFs is 0 and is equal to algebraic sum of product of currents and resistances of the resistors. So, it is now RHS part I1P, right, positive or negative. See, current and the direction of traversal are the same. So, it is plus I1P, getting plus I1P. Now, moving ahead, look at this, Ig and the direction of traversal are one and the same, and hence Ig, I have considered G itself as the resistance of the galvanometer, and hence it is IgG, positive IgG or negative IgG? It is positive IgG. Why? Because Ig is in the same direction as of the direction of traversal. This is my direction of traversal inside the loop. This is the imaginary path. Okay. So, it is plus IgG. Moving ahead, the next, okay, A to B over, B to D over, now D to A. Now, in this part of the circuit, we have a resistance R through which the current I2 is flowing, but this current is flowing exactly in the opposite direction of my path, right? Like this, clockwise I was going, this just came exactly opposite to me. So, I should now consider minus I2R. Clear on that? Good. So, it is minus I2R and I reach back the point A, and hence the loop is complete now. Clear on that? Good. Now, similarly, this is the one loop that we have considered, and the second loop that we are going to consider now is B, C, D, B. Okay, like this. Right. Now, I can say applying KVL for the loop, it starts from B, B, C, D, B. Okay. Applying KVL for the loop B, C, D, B. Now, I will start from B again. If we need to stick with the, if you want to stick with the law of KVL, Kirchhoff's voltage law, it says algebraic sum of EMFs in the loop. Is there any cell here? No cell, no source of EMF, and hence the entire LHS part is again 0. Now, the RHS part is the algebraic sum of EMFs is equal to algebraic sum of currents and the resistances. Now, I will start from B. You look from B to D, what is happening here? you have current I3 flowing through Q, right, like this. Now you see what's happening here. I3 is flowing in the same direction of my propagation or my path like this, and the resistance through which it is flowing is Q, right. So same direction and the current is I3, resistance is Q. So I should put plus I3Q, right, clear on that? Plus I3Q, because I3 is in the same direction of traversal, Q is the resistance. Now in the loop B to C is done, C to D. Now look what happens. I4 is coming exactly opposite to the direction of my traversal like this. I4 is like this and I am coming like this. So I4 is opposite to the direction of traversal, and hence I should put minus I4, yes. Now after point D, so this much is done. Again moving ahead, you have current Ig flowing in the opposite direction through the galvanometer, which has the resistance G, okay, because galvanometer has the resistance G, and you are going exactly the opposite way. So it is minus IgG. Okay. So these two are the expressions that we get. Let me call this as equation 1 and this as equation 2. These two are the expressions that we get after applying KVL for the loop ABDA and KVL for the loop BCDB. Okay, good. And now when the network is balanced, okay, what happens when the network is balanced? Okay, when the network, Wheatstone's network, okay, when the network is balanced, what do you mean by a balanced network? Current through the galvanometer is 0, Ig is equal to 0, right? So now you observe here, when Ig becomes equal to 0, what is the relation between I1 and I3? Look here, I1 is the current which was coming here, and this I1 split into Ig and I3, right? So when we apply KCL, Kirchhoff's current law, the first law, for the node, because you know that KCL is applied for the node, not for the loop. Loop is for the KVL. So when I apply KCL for the node B, I1 is the current flowing into it, right, is equal to I3 plus Ig is the total current flowing out of it, right, because this is what KCL says. Total current entering the node is equal to total current leaving the node. So I1 is equal to I3 plus Ig, right. This is when we apply KCL for node B. This is what we get. And similarly, when I apply KCL for point D, look at this. What is the total current entering? It is I2. Ig is also coming, right? I2 plus Ig is the current entering, right? And I4 is the total current leaving, right? So these two are not given in the reference, but you need to mention this, okay? If you mention this, then the derivation will be complete. I mean, it's not like there won't be anything left in the derivation, it is going to be complete. So KCL for point B will give you the equation I1 is equal to I3 plus Ig. It's very simple. Total current entering the node is equal to total current leaving the node. Okay. Now, when the network is balanced, what happens to the first equation I1 is equal to I3 plus Ig? Ig is 0 and hence we get I1 is equal to simply I3. And what happens to the second equation? I2 plus Ig is equal to I4. Ig is 0 again, so it simply becomes I2 is equal to I4. Okay, clear on that? Good. Now, not only those two equations, there will be changes happening to these two equations also. What are the changes that we see here? In the first equation, we see that 0 becomes equal to, look at this, Ig is 0 and hence this term vanishes, right? And what you are simply left with is I1P minus I2R, right? This is the first equation's changed form after the circuit is balanced, okay? So, this itself is the balanced condition. Current through the galvanometer should be 0. Now, coming to this one, again 0 is equal to, this term vanishes and hence I will be left with I3Q minus I4S, right? Now, let me bring this term here. Upon interchanging, I will get I1P is equal to I2R, and upon interchanging these two, I get I3Q is equal to I4S. Let me call this equation as equation 3 and this as equation 4. Now, dividing equation 3 by equation 4, okay? When I divide equation 3 by equation 4, I get, look at this, LHS by LHS, RHS by RHS, I1P by I3Q, right? I1P by I3Q is equal to I2R by I4S, right? I2R by I4S, right? This is the equation that we get when we divide equation 3 by equation 4. Now, what is I1 and I3? The relation between I1 and I3 is this. This is when again the network is balanced. So, when the network is balanced, I1 is equal to I3. So, I can cancel them. Similarly, I2 is equal to I4. I can also cancel them. So, I2 and I4 gets cancelled, and hence finally I will be left with P by Q is equal to R by S, and this is the balanced condition of the Wattsons network expressed in terms of the resistors connected. Okay, you have 4 resistors P, Q, R and S. Now you have the relation which connects those 4 resistances, right? And the condition that you should remember is this relation is valid when the Wattsons network is balanced and vice versa, which means when this is the relation of the Wattsons network, then we can easily say the network is balanced. Clear on that? So, if this is the condition, we can say the network is balanced. If the network is balanced, then we can say this will be the condition, and hence we can easily get any one of the unknown resistance. Like if you know the resistances Q, R and S, you can easily get P. Okay, that is the practical application or advantage of that. So that the rest you should make in such a way that you should have the combination of resistance chosen R, S and Q in such a way that the current becomes 0. Okay, that can be seen after when you observe the galvanometer. That is not a problem. When the galvanometer does not deflect, we will get to know that the current through the galvanometer is 0 and hence the network is balanced. And we should see what resistors connected in the arms making the galvanometer's current 0, and those resistors are all mathematically connected in this way, P by Q is equal to R by S. So, this is the end of the derivation. So, this is an important derivation which is regularly asked, normally recurringly asked in board examination, and again very important one. Okay. And the resistance of the galvanometer will not affect the condition here. Okay, you choose whatever the value of G here. Okay, that will not affect, okay, the balanced condition, because G doesn't exist. Once Ig becomes equal to 0, once the condition is balanced, G doesn't exist anywhere. So it doesn't matter the amount of resistance that the galvanometer has, that resistance will not affect the actual balanced condition. P by Q is equal to R by S. Clear on this? Good. And another extra point after the derivation is as follows. When you if you replace the galvanometer and the cell, which means you put the cell in the place of galvanometer and galvanometer in the place of cell, then whether the condition of the balancing will be changed or not? No. Okay. Even when you change the position of galvanometer or replace the galvanometer and the cell, the condition of balancing will still remain the same, which is P by Q is equal to R by S. Let us see how does that happen. See, when I change it, it is somewhat like this, right? Here comes the cell and here comes the galvanometer, right? This is what changing the circuit means, right? In the same circuit, AB, CD, PQ, RS, right? And now I can just change the way of looking into the circuit. I can just rotate the circuit. Okay, that doesn't affect the electrical property. So if I rotate it, point A comes here, point B comes here, and C here, D here, right? Now I have the galvanometer between A and C, right? The same network I am going to write. I have the galvanometer between A and C, and I have the cell between B and D, right? So between B and D, I have the cell. Now look at this. Where are PQRS? Okay, just a minute. Sorry for this. So here we had PQRS. So between A and B we have P, and between B and C we have Q, between C and D we have S, between A and B, between A and D and A we have R. Now what is the balanced condition for this network? This is, let us assume that this is a different network now. Let's say yes, it is a different network with say EMF, the cell and the galvanometer interchanged, replaced. Now what is the balanced condition? For this, the balanced condition is, look at this, R by P, right? P by Q, here it is R by P is equal to R by S. Instead of R by S, it is S by Q, right? The balanced condition for this network after interchanging the cell and the galvanometer is R by P is equal to S by Q. Look at this. You just make few rearrangements here. Send this P there. It will become P by Q is equal to R by S, which is the same condition before we change the cell and the galvanometer. Clear on this? So even if we change the position of cell and the galvanometer, if we interchange the position of cell and the galvanometer, even then the balanced condition remains the same. Okay, so that doesn't affect the balanced condition.